So let me tell you a little bit about this project and where it came from. So I'm going to tell you how to put your meetup on the map, literally, not figuratively. This is joint work with my friend Alan Briggs, who's also down in the DC area, and he'll give you some logos and tell you about me and tell you about him. So Alan, he works for a company called Elder Research, which is a mostly federal contractor that does predictive analytics and data mining for the federal government, like fraud detection, stuff like that. Alan is really active in the professional community for operations research. Informs is the name of that national community, Operations Research and Management Sciences. I've got my arm twisted, so I have a machine learning background. I've got my arm twisted. I'm actually on the board of the local chapter in DC of Informs, despite having no serious OR background whatsoever. In fact, this talk is not statistical really at all. It's actually an OR talk using R. And so a lot of what I'm going to present is stuff that Alan put together for when we presented this presentation previously. Once to the DC knockoff of this meetup, so we have Statistical Programming DC, and then also for the Maryland chapter of Informs. About myself, so I work for this company called Centrano. We do predictive analytics and software for large enterprises. I also run the Data Science DC meetup down there. If anybody who's ever in town and wants to give a talk, please let me know. And we also have an umbrella organization that runs currently 6 meetup groups called Data Community DC. We have a blog and stuff like that, which you should check out. So the origin of this project actually has to do with Data Community DC, and I'll mention that in just a second. So I'm going to start out with like maybe 10 minutes worth of presentation here in this sort of normal PowerPoint format, and then I'm going to move to running through several hundred lines of R code really, really quickly. So let's start with the non-code part. So I'm going to give a quick introduction to the problem. Looking at this issue of where should things be on a map. So it's going to be a very simple location problem, and we'll walk through that. I'm going to give some history of where this problem originally came from and what some of the variations are. And again, this is a really fundamental operations research application. Thirdly, I'm going to give you some specifics. So what happened is a year or so ago, we did a survey of people in our meetups, and we asked for a whole bunch of things, and one of the things we asked for is zip codes of where you live and where you work, which, if you think about it, gives you some sort of approximation to a commute line. And the idea that I'm going to show you tonight is that you can use that information to come up with some recommendations for where a good place to cite a meetup might be based on those responses. And since you guys were nice enough to provide your zip codes as well, I'm going to show you where Jared should be scheduling meetups. And finally, really quickly, I'm just going to run through some examples of the facility location problem, which this is a very, very simple example of. Okay, so to get started, say 2 people, roommates, whatever, Alice and Bob, are trying to figure out where to live on Manhattan, and Alice lives up in Inwood. It's actually where I lived for about 6 months or so when I first moved to New York. And Bob works in the financial district, so opposite ends of the island. Where do you think that they should live? Yeah, Midtown, okay. Yeah, so, basically Central Park West, why not? Yeah, that's right. That is where they should live. Now what happens if we have a different scenario, which is every day Bob has to go to work downtown once, but Alice has to make 2 trips. Has to go from home to work again. Now where should they live? Washington Heights, yeah, maybe Harlem, something like that, right? Sounds good. Yeah, no. Nobody gets this right the first time. It's not intuitive at all. So here's what's going on. The right answer is if Alice has to make 2 trips, she should live where she works. She should work from home or something like that. So there's 2 units, 2 Manhattan distances for Bob to commute, and Alice has to commute 0, right? So the answer here is 2. But if they live in Washington Heights or something like that, Bob has to do 2 2/3 trips, and Alice has to make 4 1/3 trips, and the sum of those is 2 2/3. So this is not an optimal solution to that location optimization problem. Okay, so where does this kind of problem come from? Fermat and others were sort of thinking, at the origins of geometry, of how do you solve the problem? We've got several points on a plane, and you want to find the one that's sort of closest to all of them. So it's like a clustering problem, or in this case, you're trying to find the optimal center of multiple sets of points on the plane. And this is in retrospect, this is really not that hard to do. You have a bunch of distances you put in typically, and depending on where you put the point, you basically add up all those distances. You can have sort of a little bit of complication with weights, so maybe some points are more important than others. But the basic idea is you're sort of maximizing this expression by finding points that give you minimizing the expression so you get the minimum cost. And so I'm going to be talking about cost functions a lot today. And there are a lot of variations on this. So in practical use, sometimes you don't have the ability to put your location in an arbitrary location. It has to be on a grid. So if you're opening a corner store, it has to be on the corner, right? So things like that. There's also single and multiple location problems. If you're only creating, one store, then you have one place to put it. But if you have opening a chain of convenience stores, you don't want to put them too close together because then they'll compete with each other. So you have to figure out how to have multiple locations that optimize everybody's utility. And then there's also capacity limitations. So for some types of things that you're trying to provide capacity for, if you put there may be too much demand locally, you might actually have to push secondary locations closer to suck up some of that demand so that there aren't like large lines and so forth. And there are lots of examples of this kind of thing. I'll mention one later on. So to be specific, what am I going to do tonight? So 94 of you provided your own zip code, 90 of you provided your work zip code. And so the problem I really want to solve is, this is a worse problem, I would say, in DC than it is in New York. In DC, we've got several sort of clusters of people, some who like to be downtown, some who like to be way out by Dulles Airport in Virginia, and some who like to be in the northern suburbs in Maryland. And ideally, we'd like to, offer a service to some of the people at least some of the time, right? We can't make everybody happy because they live too far apart, but at least sometimes we like people to be able to attend events. And so in theory here, I'm looking for three locations that I can rotate between, and I'm going to do this with a minimum problem of minimizing the sum of the minimum distances, I'll look at that a little bit later, to the commute lines. And here's a sort of a preview of those commute lines on top of the map. I'll have a version of you in just a second. And again, the intuition here is we want the location to be close to you or close to your commute at least sometimes. And Alan did a good job of this slide. I'm just going to sort of hand wave a little bit. There are a lot of applications of this in industry and government and other things. So IKEA is an interesting interesting example. And if you think about IKEA for a second, you're like, wait, the idea is to make it convenient for everybody to go to the store, right? You've all gone to IKEA in like Elizabeth, New Jersey, and it's not convenient. So what's up with that? So IKEA actually is a more complicated cost function because of their business model, which is they need to have an insane amount of stuff in stock all the time. And since there's a small number of stores and they merge things, they never want to run out of anything, which means inventory costs and real estate costs are a huge driver, which is why you have to go to New Jersey or College Park or something like that to go to IKEA. Gas stations and electric charging stations are interesting. So historically, there was no optimization problem to solve when gas stations were built, in the maybe 20s and 30s. Any small business person was like, hey, I can open a gas station, and they opened it wherever, and some of them went out of business, and some of them didn't. And so there are a very large number of gas stations. For somebody like Tesla, they get to decide, hey, I'm going to open a charging station every 120 miles on this interstate so that you will not run out of battery when you're trying to drive from the East Coast to the West Coast for some promotion, right? So they're doing this optimization problem explicitly right now, and it's, at some level they're going to be more efficient about the layout of charging stations. City bikes, bike share in DC. Lots of optimization problems. Where do you put the bikes? What routes do people use? There's also optimization problems that are sort of a different category of things about rebalancing, which is sort of as big a problem here as it is in DC. So lots and lots of optimization problems, many of them based on facility location. Any questions before I move on to some code? Okay. Okay, so we're going to make this available afterwards or later or something like that. But I'm going to basically run through this very quickly. Please interrupt if you have any questions, but I may say, don't really have time because I want to get to the end to get to the punchline. So this is a knitr document, fairly obviously for those who have used it. And I sort of talk about a bunch of different packages. I'm actually kind of curious how many people use knitr. Third. How about some of these other libraries? ggplot2? Yeah, 2/3 or so. How many people use the zip code package? Like 3. All it is a data set, but it's handy. The plier package, half. Compiler, a few, yeah. Compiler speeds up functions, although I think it does so less than it used to. I think they've sped up the non-compiled code a fair amount. DE optimization. One person in the back. Okay, good. How about the RMaps package? 2, 3, right, 4. So this is like, what, 3 weeks old or something? It's seriously alpha code. A lot of the stuff I wanted to do today, I couldn't really actually pull off in RMaps. So you'll see a little bit of this in this demo. Previously, I used ggmap, which is sort of an overlay of ggplot2. It is fantastic, but for this kind of demo, one of the big pluses here is that RMaps is going to let you zoom in and out and scroll around, and so there's big advantages for interactivity. Anybody use the mud cell package? If you use ggplot2, you're using mud cell under the scene, so it's how Hadley figures out what colors to use in a lot of those automatic sort of nice gradients and stuff. Okay, so what do I do? Jared conveniently emailed me a CSV file with a couple of columns and the zip codes. And so this first block is basically just bunching that code. So I read in the data, I rename things to be easier to type. I deal with a very typical problem with zip codes, which is that whenever somebody exports them, they drop the leading zeros, even though they're not numbers, they are character strings. So I put those back. And then I load the zip code data and join everything back up. And I do a little filter to get rid of basically my data, because I commute from the middle of DC to sort of near the White House. That's not very helpful for your guys' problem. So restricting the data a little bit, there was 4 or 5 other people who were, whose data was quite outside the New York area. And so this is what the top of the data frame looks like. So I've got zip codes for open work, cities and states, which I'm not using at all, but they're useful just for a little bit of context. And I've got lats and longs for both locations. And there'll be NAs, so you can see here with their NAs for the work locations if you did not provide those. Okay. Incidentally, nobody here's from Connecticut. Okay, so really simple things you can do. These turn out to actually be really good in some ways. So the easiest thing to do is to look at simple summary statistics, mode, mean, and median of those work locations. So this is all I'm doing. I'm looking up the most frequent work zip code and pulling its lat and long. And then I'm doing a median independently on lat and long. And then I'm doing a trim to mean for that long as well, and dumping those into a data frame. So here's the results. Not super obvious how to read that, but interestingly, they're quite close together, as you'll see when I actually put them on the map. So here's the first block of stuff where I'm trying to define functions that use R maps. And I'm going to go through this one a little bit slowly and the rest of them a little bit quickly. But the basic idea here is that I have a function that takes this really simple data frame, and it has to generate, in this case, I'm going to generate GeoJSON. Who's used GeoJSON? GeoJSON is amazing. So you write a simple JSON structure, which is easy to do in R, it's easy to do in other languages, and then a bunch of applications will magically put your stuff on a really nice interactive map. So CardODB will do it. R maps will do it. Leaflet, which I'll be showing. GitHub, if you drop GeoJSON in GitHub as of whatever, 3 months ago or something, it just shows up as a map. Amazing. So if you do anything with geography, you should learn GeoJSON and tools to work with it. So I'm creating this sort of nested list thing that says that I'm going to put a point in a particular location, and then inside the map with markers function, I say I'm going to create a new leaflet object. So I mentioned leaflet. How many people know what leaflet is? Great. Okay, so leaflet is a JavaScript package for working with maps. It uses OpenStreetMap data, so it does not have the commercial restrictions that Google does. So you can use it for your bank or whatever. And it is very easy to work with. It's very easy to draw things on the maps. There's a large number of different sort of looks and feels that you could put on the maps. It's very flexible. It's quite fast. Highly recommend that if you're doing sort of front-end work presenting stuff on maps. And now with the RMaps package in R, you can get access to that when you're building things like reports like I'm doing today. So I create a new sort of leaflet object. I say where I want to put it. I can sort of default to Times Square because Times Square is obviously the center of everything. And I'm going to show you this tile layer, which is basically what it looks like. That's really cool. So I don't know whose thing it is, but they have a bunch of these, and the toner is a really nice black and white one. It's great for presentations like this. And I take that data frame. It's actually a typo here. It works, but this ideally should be AL block. And I basically create a marker for each row in that data frame, stuff it into the create a list of those things, and then send that to a GeoJSON function that RMaps provide, which basically just copies what you provide, does some munging, and sticks it into JavaScript, which then gets run when you view this document in a web browser. There's also a bit of actual JavaScript here. This is really kind of hacky, but it's not really clear how else you can do it. So if you pass an argument, it will interpret this as just text and dump it directly into the JavaScript, which is not super secure and is really hard to sort of debug. But this is what you actually need to make things like pop-up buttons work. Okay, so as I said, that's the basic idea. And I'm going to use the same trick of exporting to GeoJSON for all of the maps. And here's what it looks like. So as I said, pretty cool looking map. It is interactive, around, I can zoom in and out. And we can look at the 3 different median and mode and so forth. I did not figure out how to make these look like nice little, boxes or things with text in them. Next time I do it, I will definitely figure that one out. For now, I can click on them and say, okay, the modal one is, station, and then the trimmed mean and median are a few blocks east of there, so south end of Midtown, sort of thing, which isn't that far from here, actually. So as I say in this document, Jared, you're not doing all that bad.
So who's creating the tile?
Yeah, so this is the Stamen thing. So okay, map tiles by Stamen Design. Do you want to look? Design Technology Studio. Okay. that was in an iframe, so I stuck that one in an iframe. Okay. Moving on. Okay, so we've got a lot of flats and longs, but we need to figure out distances. And in New York, degree of lat and degree of long are like 40% off. Anybody can keep cosine in their head? Yeah, something like that. Here's the really fancy way to do it. So the fossil function, which is literally a package for people who work with fossils, has, for historical reasons, the function that everybody uses to find the distance between 2 points on the globe. And so this is the Haversian function, which computes that. It's a little bit fancy. It does some math. It knows that the Earth is spinning, which means it's wider than it is tall, that kind of thing. This is just a copy and paste of that function, so you can see it. And so what I'm going to be doing over and over for the rest of the talk is defining cost functions. So the general form of a cost function looks like this. So this is the point-to-point cost. And the idea is for each one of you, you have some cost to travel to a particular location. And so that target location is the longitude and latitude that I'm going to pass in. There's also going to be a data frame. That's the data frame I showed you before, or a version of it. So there's columns for home latitude, home longitude, and work lat and long. And so all it does is it takes the, sort of unpacks the data frame, passes that to the distance function, which is vectorized, and then computes takes those distances, rescales them to make the numbers not be in the zillions, takes square distances to sort of penalize being far away, and then sums them up. So nothing very fancy here. Sum of the squared costs, or sum of the squared distances is my sort of simple cost function. Make sense? So I chose 3 venues. So I know that you guys have been at Columbia, and I know that you guys are here. And if I remember right, has this Meetup been at AOL?
A long time ago.
A long time ago it was AOL. Okay, great. I guess right. Because one of your other locations is like a block from here, and that was not very interesting, so I decided not to. Okay, so I created a data frame which has the locations, which I just looked up, Google Maps of those 3 venues. And I create a data frame, and for each sort of row of the data frame, I call the point-to-point cost function. And I end up with a data frame that has, for each one, a cost of these kind of arbitrary units that are based on square distance. Okay, so they're not super far apart. Pivotal is smallest, small cost is best. AOL is a little bit worse. It's too far south for some people, and Columbia is a little bit worse than that, and too far north for some people. Okay? So I'm not so good at reading lots and longs, as I said before, so I did another thing which lets me plot circles and give them different colors. This is kind of ugly, but handy. And so now, here on the map are color-coded with sort of a rescaled version of the costs, the 3 locations. So zoom in a bit, so we've got, we are here, AOL is down there, and Columbia is way, way up there.
Another way to compute the distance function might be to put those pairs where you're going to and put it to Google and say that you're going by subway and see what the time is by subway. And that
Yes.
might be.
No, you're absolutely right. So what I'm showing you is I'm showing you pro-flies distance, which is sort of good enough for government work. Although the government would probably pay Booz Allen $10 billion to do something extremely overwrought to get exactly the same answers, but they would take into account exactly what you said. So for every time they evaluated that cost function, they would have to go ask Google, or more likely some other provider.
Drive is what they do, right?
What did you say?
People that drive.
Yeah, that works too.
Like PLS does for baskets of goods.
Yeah, so the problem with that is if you're just only doing it 100 times, it's not a big deal, Google doesn't care. If you're trying to evaluate that for every little slight nudge of the locations, then you're talking tens, hundreds of thousands of evaluations. Doing this sort of subway distancing, that gets expensive, often literally.
Seems to be not that much difference in terms of what the costs are.
Yeah, no, it's true.
Give me some intuition in terms of what's happening there. Because it seems it's a flat max, And how big is the flat?
Yeah, so it's a flat max for work zip codes. I think part of it is the zip code issue. So, zip codes are not, I mean, I
So
can't
what do you
remember,
mean,
they're,
the center of the zip code?
yeah, zip code centroids.
Okay.
So if I had actual addresses, it would probably be a little bit, a little bit different. My guess is not hugely different. There are some zip codes that are kind of weird, but I don't know. Yeah.
I was just going to say that rather than doing all those calculations for every nuance of the whole subway system, just distance to a station might be something that you can use to
Okay.
tweak a little bit, but I would suspect that you get something very, very close.
Yeah, and for this particular thing, just the point-to-point distances, I'm guessing that it doesn't really matter that much. But yeah, so like a statistical problem, your domain knowledge is hugely important to help you set up the problem the right way. In this case, whoever is paying the bills for this optimization problem, so Jared, didn't pay me enough to do something. Okay, so like I said, some of the costs, distance on a sphere, that's actually kind of overkill. So later on, I'm going to drop that and just say, well, okay, I'm going to take the tangent on the sphere and say that's close enough. But as I said before, it's not a great solution if a substantial portion of your audience is excluded because they work way uptown or in Brooklyn or in New Jersey or something like that. And it would be valuable to, as a meetup organizer, to provide the service of at least giving them something to go to sometimes. So that's why I wanted the home zip codes as well, not just the work zip codes, so that I can find places that are accessible at least sometimes to everybody. So what do those commutes look like? So here's a map. I do them on in orange on this map here, and there's some people. Are they actually here? Somebody up on that. They probably had a free thing earlier. We're here to pick it up.
They want a prize, they didn't claim it.
Yeah, exactly. Right. This is somebody up in the Bronx. There's people from New Jersey.
Are these plotting commutes? Is it each point?
Yeah, each line is a commute. There aren't a lot of people with identical commutes. I think there are a couple here that I saw that are darker than the others. Since I'm doing centroid to centroid, if you live and work right next to somebody, you have the same commute line. When I did this before, I had a little bit of randomization. I didn't have time to do that today. But you can see like weird little artifacts like this little triangle here. That's because I'm using centroids.
Yeah, I'm just curious, what does it look like if you live and work in the same zip code?
Yeah, so it looks like this guy right here. That might be live and work in the same zip code. It might also be I don't work, so I'm retired, I'm unemployed, whatever. And so I can zoom out a little bit and see some of the farther right context. There's some people who maybe have that, up here in New Jersey where it's very pretty. There's somebody down here by Princeton. And zoom all the way out. Either there was a typo. Is there somebody here actually? I can't remember either lives or works in Arkansas. Okay. All right. So next thing I'm going to do is I'm going to write a function to do the point to line segment computation. So this is a little bit more difficult than point to point. So in your mind's eye, think about it. So you've got a line segment in space. You've got a point. And sometimes that point is closer to some point on that line segment than to either of the ends. And then sometimes it's closer to one of the ends than to somewhere else. So you can imagine if you've got a line segment, you've got a thing that looks like a bacterium or something like a kind of a racetrack around it. And so the idea that this computation does, which I stole from somebody's answer on Stack Overflow, that's how programming works, is so basically what you do is you find the tangential closest point on the line extended to infinity, and then you figure out where proportionally from one end to the other it is, and if you're off one of the ends, then you just use the point-to-point location. And if you're curious, we'll look back for later, I'm not going to go through it. It is not super complicated. And actually, R has some nice constructs for doing this. So the vectorized if else is kind of a pain to write in some other languages that don't like that kind of thing, but it's really trivial in R, which is nice. Oh, and then I also have, yeah, the NA here is to catch the ones where there's no work location, and just defaults to the home distances, which I previously computed. So like that, I wrap it all up in a little wrapper function, and then I'm going to compute the costs of those recent venues, AOL, Colonial, Pivotal, and drop it on the map. Map looks exactly the same, so I'm just going to show you the data frame. And so now, one thing to notice, I don't have an intuition here, the difference between the goodness or badness, however you want to look at it, of the cost function has sort of blown up. So the relative distance, the relative amount that Pivotal is better than AOL compared to Columbia is about the same, but now sort of the distance from 0 is different. So anybody actually has an intuition about that? I'm curious. But so you end up with the same result. So point-to-line segment, Pivotal is best of the 3, but hey, maybe we can do better.
Well, look where all the lines were, right? They were all to the east and south.
Yeah.
Like, there were very few lines going north.
Yeah, well, some, but yeah, that's true. But there were also those points out in sort of, you know, the nice part of New Jersey.
But a lot of lines east and
Yeah. Okay, so, you know, what does the overall surface look here? So you could imagine taking a point and doing like a little grid search over, you know, the whole area, and just seeing what that point-to-line segment cost function give you at all those points, and that's exactly what I did. In the previous version of this talk, I had a really nice sort of gradient overlay on a map that looked fantastic. You don't get that, sorry. Instead, you get a bunch of circles on top of each other. Looks like something very bad happened to New York. Blue hurricane or something. Wow. And my colors are great here, right? I need to work on this, so sorry about that. As you saw from my Meetup Dice thing earlier, I'm not really that good at JavaScript, so this is kind of painful. But anyway, you can kind of see here if you squint that you know that there's sort of a nice area here in the middle. Technical term. I mean, the only thing that's really interesting here for this map is that it's not a perfect circle, right? So, like I said earlier, there's sort of a general pattern of where people tend to be. And so it's better to move north and south than to move east and west, which is kind of obvious if you actually have any domain knowledge of the island of Manhattan. But it's also reflected in the data, which is nice to see, right? Okay, so south of Midtown, good place for meetups. All right, so let me do some actual optimization. So I'm not an expert in optimization. I think I have decent intuition here, but lots of people, raise your hand if you know more about optimization than I do. Yes, you do. There's definitely people in the audience who knows more about optimization than I do. So I grabbed a nice web page to describe one of the standard continuous optimization algorithms. This is the Lbf optimization algorithm. It's what you get when you run optim in R. So let me just step back really quickly about optimization. So I get the feeling that many people here do statistics or machine learning, things like that in your day-to-day job. Under the hood, what's going on, except for the very simplest sort of least squares problem, under the hood what's going on is an optimization problem. So there's some objective function, you've done lasso regression or something like that, they're written out, and under the hood, there is some function that has to evaluate that function over and over to jigger the parameters around until the number stops moving, right? So that's an optimization function. The academic area that really focuses on numerical optimization of this sort is operations research. And they are very good at both the continuous function optimization as well as things like optimization when you have integers. So it can't be continuous, it can be 1 or 0, for example. And you can the quality of those optimization algorithms has gotten really insanely good. It's grown much faster than Moore's law over the last 40 years. So I know nothing about that, so I'm just going to hand wave an elder beat, often called the simplex algorithm. The idea is if you've got some points on a plane, this is sort of a simple case, you can sort of calculate the goodness of those points, and based on that, make some decisions about where to put the next point, which is where you're going to evaluate the cost function. And so you can sort of, like, if the one over here is bad, then you can sort of pick something in the middle, or maybe you sort of reflecting in the other direction, or maybe you sort of contract. So what you end up doing is you end up sort of flipping your way this triangle over the surface. And eventually, you find an area where moving in any direction doesn't help, and then you stop and you say you're done. For some problems, this will always converge to the same solution. In general, it will do so if the surface in the high-dimensional space, which is impossible to think about, is convex, which just means that if you drop a marble somewhere in your high-dimensional space, it always ends up in the same spot. So I'm not totally sure that this is exactly a convex surface, because there are definitely, if you think about individual line segments, any point on that line segment has the same cost value. So it doesn't, if you put the meetup in my house or my workplace, those are both fantastic. So there's stations when you sort of try to optimize this problem. So I did this a few times, started with the existing venues. I ended up in the same places all the times. And what is the answer? Well, the answer is a few blocks north of here. So a bit of it. So based on the point to line segment distance, right, so it's, 30th between 56 right off Broadway. Not a very nice location for me.
Ace Hotel. It's over there.
Actually, this is what's there. TSR Silicon Resources with a sign from like 1979.
It's all those perfume shops. Those guys with like the bootleg car.
Yeah, I don't
Ace
know.
Hotel is right there.
Yeah.
Someone get a free room.
I definitely think you should take over Silicon Resources, Jerry. Okay, so multiple locations. As I said, the real goal is to find several different places. And so I'm defining a new cost function. This is the point to line segment with n, sort of multiple locations here. My code here is terrible, I apologize. It gets the job done, which is what matters. So basically what it's going to do, somewhere in here, there's a min function which takes the results so there's 3 results for every person and finds the minimum cost of that matrix. And I do some really horrible punching to get stuff in a format that the optimization function likes. So the optimization function wants a vector of numbers. So it's 6 of them, 3 pairs. And so somewhere in here, what I'm going to do is I'm going to get the cost for 2 different triples. So a triple is like a triangle on the map, right? So if you rotate it between here and AOL and Columbia, I would draw a triangle on the map, and that triangle as a whole now has a cost, not the individual sort of corners of the triangle. The triangle as a whole has a cost, and different triangles will have different costs, right? So I'm going to show you the results of 2 triangles. One is what I just said, the triangle of pivotal AOL and Columbia, and the other one is pivotal AOL and that spot on 30th Street. And here's the results. So you can see Columbia's way up here. The new sort of single point optimum is down here. Which one of these triangles is better? The blue one is better, even though it doesn't have the single optimal location. It's because the people who live and work uptown find it much easier to stick around Columbia than to come all the way down here. And these 3 locations are within whatever, 10-minute walk of each other. There's really not that much difference between juggling around those 3 locations. So in general, the intuition here is that it's good to have, in the multiple location problem, to have your venues pretty far apart, right? Because they're catering to different customers. Am I on time? No, not bad. so if you're trying to do this 3-location thing, I'm now trying to optimize a vector of 6 numbers, 6 lat long, or 3 lat long pairs. And in the single location, it didn't seem like I had to deal with local minimum, but I wonder if I might have to deal with that problem here. So my points are not, the points I'm searching around are not all sort of like clustered in that really nice pocket in South of Midtown. They might be farther apart, maybe up by Columbia or Brooklyn or something. So let me just try a brute force thing. And I'm going to use a different optimization algorithm. This one is the really memorably named Lbf Gsd Algorithm. This is the reason I'm using it is because I actually put bounds on the parameters. So it's not going to go searching off in like Alaska or something. So I'm going to draw a box, half a lat long degree on each side, so 100 miles, something like that. And so I'm going to call the optimum function again with some starting points of those 3 pairs. Use the Lbf Gsd, give the lower and upper box coordinates, upper left, lower right, or something. You can see I turned on the trace, so you can actually see the optimizer saying, so it's running 10, 20, 30 times, and trying to get that number smaller and smaller. And this is a little bit disturbing. So I only ran it 5 times because you don't actually, to prove this point, you don't actually need to run it a large number of times. But it's getting really different final values, and sometimes it's terminating without merging. Like this is a little bit distressing. So let me show you the results and then back up briefly to the algorithm. So it's got these sort of 3 pairs of flat longs. This is even worse than before in terms of eyeballing it to see what the numbers mean, because these could be in arbitrary permutations and still be the same triangles, but they turn out not to be. So if you turn these into Json, you can see several different triangles that are not even close, right? So they mostly have something here in Manhattan, but then like way out here, and they're really, really different, right? So they're not converging on anything like similar results. And some of them are really weird. Don't want to stop there.
Question, did you get rid of that, the guy in Albertson?
I didn't, but it actually doesn't matter because his other end was in Bay Ridge or something. Okay, so not that far. Okay, I was just going to say Lbf Gs. So BFGS is a kind of Newtony thing, so it's estimating the curvature of the surface. If I'm wrong, please correct me. The idea is that you sort of iteratively guess what the curvature looks like, sort of jump in the direction that seems to be a good sort of downward direction, and then you sort of update your estimates iteratively. This guy first.
I don't know if you know, but for the convergence problem, there is an argument in the Optim package where you can set the maximum number of iterations.
Yep.
Yeah, so
Yeah, that's a good point. So none of these optimization problems, none of this type of optimization problem, can you say how long it's going to take? So is that your parameter? Yes?
My understanding is that you're just looking at the distance to the nearest point in your triangle of 4 points. Is that correct? In terms of you're getting your distance to the nearest mean. Is that correct?
For every person.
For every person.
For every person, I'm saying, what is the distance from the 3 points to their commute line segment?
Right.
Adding those up, and then for that gives 3 numbers. That gives 3 numbers for each. What you end up with is a matrix. It has a number of rows are the number of people, and it has 3 columns. One is the cost of going from their commute to each of the 3 locations. Then row-wise, I take the minimum of each of those
Got it.
and sum them up.
Yes, to the nearest. So what I was wondering is whether you might get more stability if you put a cost in there saying, let me try to spread these 3 points or 4 points as far as possible away from each other. Whether it might be a more stable solution.
I'm not sure. What I thought you were going to ask is, I'll answer the one I thought you were going to ask, is maybe what you want to optimize is like, the average of the 2 better or something like that. Why am I picking the mid? Maybe I wanted to sort of have a guarantee that at each location is going to be pretty good for a substantial number of people. So that depending on your business problem, there are different sort of costs that you could add on. So you could try and optimize something other than the minimum. You could try and add additional types of costs that would make sense in doing this way. Okay, I want to talk about Lbf Gsd anymore. All right, so I want to talk about global optimization. So the previous two algorithms, Lbf and the Lbf Gsd thing, are continuous optimization problems where at each step in the algorithm, they have one point in the high-dimensional space that they're trying to optimize. And they circle around, and maybe they have a little bit of a memory that they're sort of trying to, the analogy of a marble rolling down the hill is correct. There's another category of optimization for this type of problem, which is related to genetic algorithms or population approaches, and they have a pretty nice intuition as well. And what that intuition is Darwinian evolution. So you think of each point as an organism or something like that, and on each generation it can either mutate, when it replicates, or else combine with something else. And so if you think of each of these points in the high-dimensional space as these six-dimensional vectors, maybe it's going to take in the next generation 3 of one numbers and 3 of another numbers. So you end up taking sort of 2 of those points and then sort of swapping the third one or something like that. And you do this where every generation there's dozens or maybe 100 or 200 different candidate locations. So you end up with there's a variation on this called particle swarm algorithm. So you think of a swarm of particles all sort of buzzing around, trying to find the best location. And it turns out in practice, this type of thing can be very effective, and compared to sort of randomly sampling the space, can get to a global optima. So even though there are maybe bumps in the surface and rolling a single marble down a hill isn't very helpful, this type of algorithm often finds the very best solution or something very close to it using a relatively small number of evaluations of the function. A relatively, maybe 15-year-old, something like that, approach called differential evolution. At each step, it uses something like that sort of triangle flipping thing I showed you earlier with Lbf. So it's combining a little bit of that idea with the sort of population idea, and in practice, it gets very good results. In this category of algorithm, there aren't a lot of nice proofs of anything, but you often, like I said, get good results. So this is really easy to call. So I have this point-to-line segment function, and I'm calling that, I'm passing that to the DE optimum function. I'm using the same box constraints as I did before, so I'm not looking in Alaska, and then I pass it parameters. Tracing is very helpful, but in this case, it would just give you like hundreds of lines of numbers, which I showed here, so I turned it off. So in each generation, the population is 100 individuals. So 100 different points sort of swarming around this six-dimensional space. I run it for up to 300 iterations until it hopefully converges. And then DE Optim has this sort of, a bunch of other parameters you can set. In fact, there's a bunch of variations of the same idea. And there are, at least, I don't have good intuitions about which one is better. The default was strategy number 2 and didn't really work very well, so I tried strategy 3. So it's kind of that kind of algorithm. And this took a while. This takes, on the 100 points, running, 300 iterations, but 100 evaluations per generation. This takes like 5 minutes or something. And most of the cost is the fact that I've written this up, the cost evaluation function in R, in a probably not very efficient way. If this was rewritten in something faster, this should have taken on the order of a few seconds. But I'm lazy, so I won't do that. So there's a little bit of the intuitions here. You can look at this later. There's a link to a blog post that does kind of a nice walkthrough. There's also a book about differential evolution. So the mutation one is pretty easy. You've got 3 points, and when you go from this point to that point, went downhill in the cost surface, you say, hey, this direction here, the screen line, that's kind of a good direction to go. What happens if I apply that direction to a different point? Now here's a new candidate point that's in the same direction. It's not quite as far because I'm being a little conservative, and now I have a new point to evaluate for the next generation. Crossover is a little bit hard to think about, so I won't do that. Okay, so a couple of plots. There's a bug in TE Hopton. You're supposed to go take the output and plot it like linear model or something to get the convergence. Actually, doesn't work in the current version, so I have to rip this stuff out of the object and plot it by hand. This is one remaining bit of ggplot in this presentation. And you can see the cost function. So this is the best single individual in each generation. It starts out around 360, and over time it drops sort of below 290 or something like that. And it's quite flat here at the end, so that should give you some justification to think, probably good enough. And again, because of the way differential evolution works, it's always trying new things. It's not sort of getting stuck in the local minima, because there's lots and lots of 100 different points in this space, so it's unlikely to get caught in a local minima, so once it's flattens out, you're probably okay. So what does the solution look like? Here it is. So 3 points, one of them sort of the lower part of Manhattan, one of them sort of upper part of Manhattan, and then one of them way out west of New Jersey. Raise your hand if you're from New Jersey, you're really happy about this. Yeah, Jared's like, man, I'm not gonna do that.
There is a New Jersey arm meetup.
So actually, where are those points? So just zoom in so you can actually see the street names. One of them, again, just a few blocks from here. Looks like this is 5th Avenue, and 2 blocks out, something like that. So very, very close.
Right around you.
I'm sorry?
It's not like right around you.
Right around Newton.
And then where's the uptown location? It's right off of 125th. So kind of.
Stat department.
What did you say?
Around the stat department.
Yeah, the stat department's right there.
Yeah. Well, it's like a couple blocks. Stat department would be right here-ish sort of thing. Yeah. Well, it's kind of close to the New Columbia Peninsula.
Actually, no, the stat department is right here. Oh, that's more expensive. It's right here. Yeah.
22 and a half.
Yeah.
Yep. Oh, that's right. And then we're over in a farm here, I think. Oh, no, there's actual streets here. I have no idea where that is. Okay, but so the interesting question is, why did it find this solution? Again, sort of repeating what I said before, there are subpopulations within the people who registered for this meetup who have commutes that don't take them very close to the little labs, that take them either up near Columbia or way out in New Jersey. And in everything else being equal, which of course is not, Jared might do well if his goal was to maximize the number of different people who are minimally inconvenienced monthly to rotate among these locations. And that's it.